So in the previous part of the lecture, we discussed that that the likelihood that the posterior distribution of the parameter W, is just P of W given the data and the hyperparameters gamma and lambda is directly proportional to the likelihood, that is probability of the data given the parameter W, and the prior information P of W given the hyperparameters gamma and lambda, right? So this is a posterior. This is the likelihood, and this is the prior. So now this is, we can divide by the normalization term, which we assume there's some constant C. So then this proportionality becomes equal sign if we divide it by the normalization term. So the normalization term is simply this C is equal to P of the data given W into P of W given gamma and lambda dW into all W. Right. So we can simplify the equation. So we have P of W given the data set X, Y, and the gamma and the lambda is proportional to the P of Y, the data given the parameter W, times the prior P of W given gamma and lambda. And we can further simplify this likelihood function, assuming that each of these samples is independent and identically distributed. So we're still assuming that each of the yi's is given by fw of phi of xi plus some noise epsilon I. So these epsilon i's are ID, as we saw in the previous lectures. Then this is equal to I equal to 1 to m P of yi given the xi and the w times the prior information P of w given the hyperparameters gamma and lambda. So we just assume that this is some constant. So we'll just, like, for the sake of simplicity, we just have equal to sign rather than using the proportionality sign. So posterior given the data D of m data points and gamma and lambda is given by this equation, right? And as we discussed discussed in the previous part, in the previous lecture, that if we have new value x hat, then we can compute the distribution y hat given x hat and the previous data set. So this is actually y hat given x hat actually independent data set. This is dependent on the data set through W. But once you marginalize over W, it is not anymore dependent on the data set. But just for the sake of simplicity, to make you understand as to what is happening, we are just having it contingent upon the data set. But given the x hat, it would be independent of the data. But once you marginalize, unless you take a joint distribution over W, only then it would depend on the data. So this would be simply integral all W P of y hat given x hat and the W times P of W given the data and the gamma and lambda dW. But as we discussed, this integral is very hard to compute, and that's why instead of computing this posterior distribution, right, this is a posterior distribution, we just find an estimate W map or maximum a posteriori probability estimate, which maximizes this posterior distribution, right? So this is same as W map is given by maximizing the posterior distribution, which is I equal to 1 to m P of yi given xi and W. So it is conditioned on W as well, times the prior information P of W given the hyperparameters of the distribution gamma and lambda. So this is what results in regularization. So once we incorporate this prior information, this Bayesian setting, we used in the previous part of the lecture, we showed that this is done using just a Bayes theorem. So this, let's suppose, if we use the same hypothesis, let's suppose we assume that yi are given by fw of phi of xi plus some noise epsilon I. If we assume that each of these epsilon I are IID, right, and this is still a linear function of the W, which would be replaced by W map, then this kind of regression is known as Bayesian linear regression. Bayesian linear regression or Bayesian curve fitting, to be more general. So the Bayesian settings allow us not just to maximize the likelihood, but while maximizing the likelihood, we can trade off using the prior information that we had on W before even observing the data, right? So to simplify everything what we have learned, so in the previous parts of the lecture, whatever we learned, it was actually required to understand how do you arrive at this formulation that we have to compute the W map. So to understand how does this this formulation comes, like W map, sorry, I should have an argmax over here. W map is given by argmax over W, multiplication of the individual probability I equal to 1 to m, P of yi given xi and W times probability of W given gamma and lambda, the hyperparameters. These are not random values, this is just hyperparameters. So this is known as the map estimate. That is the maximum a posteriori probability estimate, because it maximizes the posterior distribution P of W given the data and the gamma and lambda. It maximizes the posterior distribution of W. So now we are going to show what different kinds of so here, for the sake of simple to link it with the linear regression, we'll assume that now yi's. So let's suppose. So first of all, before doing that, let's suppose you can compute. Let's suppose we can solve this optimization problem. Now let's suppose we obtain this W map. Right now, we can ask again the same question. Given some new data point x hat, can we compute its target value y hat? Right, from this truth. The answer is now simple. Assuming that that we are learning a linear functional mapping, so now y hat would be given by f W map of phi of x hat. And if this is linear, then we can use phi of x hat transpose times W map. And this regression problem, so we are doing a regression with prior information. This regression known as Bayesian linear regression. Right. And different choices of this distribution over the W, the prior distribution W, will result into different kinds of Bayesian linear regression. Right. So this distribution is regulating, as we have seen in the earlier part of the lecture as well, that this prior distribution is actually regulating the values of W. So it is saying, okay, you can compute any value of W that maximizes the likelihood, but then there's a trade-off, right? If you keep on increasing this will decrease. And if you keep on increasing this will decrease. So there's a trade-off, a nice trade-off between the two. And this is what the optimization problem solves. So the different choices of lambda and gamma will regulate how strongly actually we believe into our into our prior beliefs that the value of W should be small or large, basically. So as we see, like gamma, we'll assume, which is a mean, we'll assume that this is mostly 0, and we will see like what are the different distributions. So earlier, if you recall the earlier part of the lecture, let's assume that the W is given by the Gaussian distribution. So now the P of W, and assuming that gamma, the mean is equal to 0, and so mean is 0, and lambda, the parameter lambda controls the covariance matrix. So the covariance matrix is given by lambda inverse I, identity matrix. So we are assuming that each of the individual components of W are independent of the other components. So this distribution is then given by lambda over 2 pi to the power n by 2 into exp of lambda by 2 times norm of W square, as in the mean is 0. Likewise, if you have a Laplacian distribution, again with gamma equal to 0, that is the mean mu equal to gamma equal to 0, and the diversity B, the lambda, right? The diversity is equal to lambda inverse, B is equal to lambda inverse. Then we have a resulting distribution over W as lambda over 2 times exp of lambda times absolute value of W. So let's use the component, the ith component of the vector W will have this distribution, and the total distribution, the joint distribution of each of the Wi's, assuming they are all independent, is just pi of the multiplication of the individual probabilities, I equal to 1 to n, lambda over 2 times exp of lambda times, which is effectively equal to I equal to 1 to n, is equal to lambda over 2 to the power n times the individual probabilities. Which is equal to lambda over 2 to the power n times exp of lambda times the L1 norm, right? So we can simplify both the equations. So we can erase all this to write it simply as this is equal to lambda over 2 to the power n times exp of lambda times L1 norm. So now we can compute the posterior. So now this posterior would be given by, so now the W map is equal to the arg max over I equal to 1 to m P of yi given xi and w times the distribution. Let's first consider normal distribution. So in normal distribution we have lambda over 2 pi power n by 2 times exp of lambda over 2 times norm of w square. And likewise, if you consider the Laplacian distribution, zero mean Laplacian distribution, then W map is given by arg max multiplication of the individual probabilities times lambda over 2 to the power n times exponential of negative of lambda times L1 norm of W. So now, as we can see, we can assuming we have assumed that still the individual data points are independent identically distributed, the individual noises are independent identically distributed. Now, same as instead of maximizing, let's call that a new function f, right? So instead of maximizing directly this function, we can maximize the log of this right hand side, right? So if we do that, right, which we'll show soon, then if we assume the Gaussian distribution over the parameter w, this will result into the optimization problem as arg max over w norm of y minus, assuming that these are Gaussian distribution, we're assuming that the noises are epsilon i's have a normal distribution with mean 0 and variance sigma square. This would be plus lambda over 2 times norm of w square. Sorry, this would be min. We are minimizing the negative log of the likelihood. So this would be arg min. And likewise, if we consider Laplacian distribution, then this would be arg min over w norm of y minus phi of w plus lambda times norm of w. So this problem is known as L2 norm regularization, regularized least squares, because we are still minimizing the least squares over the dataset with an L2 norm over the parameter. Here we minimize the least squares over the dataset and the L1 norm of the L1 norm over the parameters w. And this problem is known as L1 norm regularized least squares. So this problem often in the literature is also known as ridge regression. Also it's known as Tikhonov regression. And this problem is often also known as the lasso. Right? But we'll just call them L2 norm regularized least squares and L1 norm regularized least squares. Right? I think the math here is simple enough. So assume you are having a normal distribution. So this would be Gaussian. You take the log of likelihood, then the entire thing will become summation. So after you do the math, it's very easy to derive that this will lead to this formulation and this will lead to this formulation. Right? So this is very simple to derive. You take the log and you plug in the Gaussian distribution over here and you will achieve these two equations. So now the question is, how do we maximize, how do we minimize this and this to obtain the W map L1 and W map L2, right? So now this is what we are going to derive in the rest of the lecture. So first, to be able to solve this problem, so this problem can be easily solved. But turns out that this is not differentiable. When W is 0, is a vector of all zeros, then this is not differentiable. So this is a non-differential convex optimization problem, and this is a differentiable convex optimization problem. And the solutions to both of these problems are fairly simple, as well as they will get a bit complicated. But we'll explain how to derive, we will derive the algorithms to actually optimize both the L2 norm regularized least square and the L1 norm regularized least squares. So we can use gradient descent, we can use sub-gradient descent, we can also use normal equations, And we can also use one of the algorithms known as IST, or iterative soft thresholding algorithm. So now let's begin with solving, with minimizing the L1 norm regularized least squares and the L2 norm regularized least squares.